So in part 3 of your Kin 425 lecture for January 20th, I'm going to introduce the Golgi tendon, organ, and muscle spindle. These play important roles in your neuromuscular system. Both are receptors and both cause reflexes. Both protect against muscle injury. The Golgi tendon organ is thought to be activated by tension in the muscle, so most likely activated when you contract a muscle, whereas the muscle spindle is activated by stretch. So this diagram shows you how these receptors are positioned in the muscle. So down here, I've got a muscle fiber. Here I've got the motor neuron that is innervated to the muscle fiber, and then you've got activity that's coming down from the brain. So there's your motor neuron. The muscle spindle is kind of located in the belly of the muscle. The Golgi tendon organ is located kind of towards the tendon junction of the muscle. So the muscle spindle, when it's activated, it sends excitatory, what's called afferent. Afferent just refers to as messages being sent from the periphery towards the central nervous system, so going from the muscle to the spinal cord. So your central nervous system is your brain and your spinal cord. So anything going towards the central nervous system is afferent. And this is excitatory afferent, which means that it's activating that motor neuron, and in turn you're going to get activation of the muscle. So stretching the spindle causes a reflex muscle contraction. The Golgi tendon organ has an opposite effect. So again, it sends afferent input to the motor neuron, but that input is inhibitory. So it's going to shut down that motor neuron, and it's going to make muscle contraction less likely. So afferent refers to going back to the central nervous system. Anything coming from the central nervous system is referred to as efferent. So it's away from the central nervous system. So in this case, the input from the motor neuron to the muscle is referred to as efferent input. And a little bit more detail here. That excitatory nerve fiber that goes from the spindle to your alpha motor neuron is called excitatory type 1A or 2 afferent, whereas the one that's coming from the Golgi tendon organ is your type 1B afferent. So a little bit confusing with the numbering and the letters there. I'm not sure why they came up with that system, but that's what those afferents are called. So one problem with this whole system is that if your muscle is contracting, theoretically the spindle would shorten, and that would result in less information about muscle length or change in length being transmitted to the nervous system. So this spindle is activated when your muscle is stretched, and it's activated if the muscle is stretched fast. So it's activated by the amount of stretch and also by the rate of stretch. And it's important, if your muscle is being stretched, to have that reflex contraction. It's important, say, in situations, for example, like maintaining your posture. Like if you're on a bus and the bus suddenly stops, and you're thrown forward, your spindle might be lengthening in that situation, and the reflex contraction would help you to regain control of your posture and prevent you from falling on the bus. So it's important to keep that spindle stretched so that it can be sensitive to changes in muscle length and send the appropriate information back to the central nervous system. So one problem is if you're contracting a muscle, theoretically you'd also be shortening the spindle, and that would result in the spindle being less sensitive and not sending the appropriate messages back to the spinal cord if the muscle is stretched. So that's what the problem on this slide represents. If the muscle is contracting, then theoretically the spindle would shorten, and that would result in less information about muscle length or change in length being transmitted to the central nervous system. So the way your muscle prevents this is that, first of all, you can see in this picture, you've got the whole muscle. You've got the alpha motor neuron is the typical motor neuron that you have in the spinal cord. When it's activated, it's going to cause the muscle to contract. The muscle fibers that are outside of the spindle in the muscle, so this could be like your type 1, type 2A, type 2X muscle fibers, they're called extrafusal muscle fibers. So those extrafusal muscle fibers contract when the alpha motor neuron is activated. Now recall the problem with the contraction of the muscle is that theoretically this muscle spindle, so this is your spindle here, your spindle would also shorten, and that would result in a loss of information going back to the alpha motor neuron about changes in muscle length. So to prevent that, when your alpha motor neuron is activated to contract your muscle, at the same time you have these other motor neurons called gamma motor neurons. They're specialized motor neurons that are activated at the same time as the alpha motor neuron, and they send excitatory input to these little muscle fibers that sit at the end of the spindle. So that's what I have in black, and those are called intrafusal muscle fibers. So they're very specialized muscle fibers that are just associated with the spindle. When they contract on each end of the spindle, they maintain the spindle in a stretched position. So despite the fact that the entire muscle is contracting because of activation of the alpha motor neuron, the gamma motor neuron contracting at the same time maintains the muscle spindle in a stretched position by contracting these little fibers on the ends of the spindle. And that allows the muscle spindle to remain sensitive to changes in length of the muscle, of the extrafusal muscle. So I've kind of tried to summarize it down there. Contraction of the intrafusal muscle stretches the muscle spindle, which offsets the shortening that occurs when the extrafusal muscle contracts. So that's pretty much a wrap on today's lecture, and I'll see you guys on Monday.